It's my great pleasure to welcome everybody to our auditorium in-person lecture series, Sea Secret, that has been here for a few years. And I'm really glad to see that we get more and more audience in person. I'm happy that people are following us on Zoom, but clearly having people in the audience is a much nicer environment that we were missing over the past couple of years. Please note that the new regulation of with COVID, we do not require the wearing of masks, but we encourage people that are immunocompromised to continue wearing them. And we ask also not to bring any food in the auditorium and not eat during the presentation. I would like to take this opportunity to thank the contributor to our sponsor to this series, which is an important one, as many of you came to realize, that we hope to be able to continue in the future. So we would like to thank in particular the presenting sponsor, the Bank of America, and the Shepard Broad Foundation, Bill Galway, that is with us this evening in the audience, Cheryl Gold, the Key Biscayne Community Foundation, the KB Life Enhancement Forum, Joan McCann Family Foundation, the William McKeehan Trust, Nicole and Myron Wang, and the Southern Glazer Wine and Spirit. Before we continue, I would like to take a moment to express my sincere condolences to the family of Marius Robinson from the Key Biscayne Life Enhancement Forum on his recent passing. Marius' support of the Rosenstiel School and Sea Secret in particular will be valued forever. Our thoughts are with you and your time of sorrow. Following on our tradition of highlighting before the main speaker of the evening, one of our alumni and or people working with us. This evening, we would like to spotlight one of our exceptional graduate students and alumni. And I would like to introduce Stephanie Wright. Stephanie is originally from Baltimore, Maryland, and kind of not surprisingly, after living a few years in Miami, now sees Miami as her normal home. I would too. Stephanie is a student in our professional Masters of Professional Science in Exploration Science. And she's working, in fact, with Ved that we are going to introduce in a few minutes. She got her BA from Transylvania University in Technical Theater and Philosophy in 2016. Yeah, great. In 2017, she became an AmeriCorps alumnus. Over the past 4 years, Stephanie traveled the globe by way of a passenger cruise liner and learned from a global coastal community while working on the cruise liner for the past 4 years as a technician. She was accepted into the MPS program at the Rosenstiel School in 2021 to pursue her interest in connecting diverse communities with science education and resources. Presently, she is a field campaign manager at the Aircraft Center for Earth Studies with Dr. Chirayath. Her work ranges from the creation of scientific visualizations, website design, building the solar electric research vessel, and many other functions. I guess that she is clearly overexploited by Dr. Chirayath. Should ask for an increase in salary, in my opinion. This summer, she will be assisting the team in the field campaign to Guam and Hawaii to validate their innovative technologies and help international communities assess and manage their coral reef. Stephanie, please.
Thank you, Dean Avasar, and thank you to Sea Secrets for giving me the opportunity to speak with you all today. My name is Stephanie, and I am delighted to present to you what a Rosenstiel degree means to me. But first, a little bit of background. As Dean Avasar mentioned, my Bachelor of Arts degree has nothing to do with science, but it allowed me to travel the world and find out what is truly important to me. So, fresh out of college, I decided to embark on a new journey with AmeriCorps and assist the Department of Natural Resources, the National Park Service, and the Army Corps of Engineers. I spent 6 months in Washington State learning science communication, how to build trails and rock walls that you can see in that video, and from the coast of La Push to the deserts of Wenatchee. Once I'd had enough of the rain on one end and the dry desert on the other, I was fortunate enough to be able to use my degree and work on board cruise ships. Exploring coastal communities and living on the sea, I was able to meet remarkable people from all over the world. It was through that experience and life on the sea and speaking with people who had lived their whole lives on the sea that I began to realize I had to do more for our oceans and more for the people that depended on them. That experience led me to Rosenstiel and the influential professors I have had the opportunity to work with and learn from. They have the breadth of knowledge and interest and skills that I hope to have, like Doctors Keen Haywood and Kenny Broad, who are leaders in citizen science and exploration. Both fields I hope to be able to use when I engage with communities wherever my path winds again. And Professor Chirayath, who has transformed this lighting designer into a solar panel rigging marine technician. Working with and learning from my professors has reinforced in me that it matters not where you came from or what you did before. Instead, what matters is how you use what you know now. With my interdisciplinary resume as a theatrical master electrician, as a content manager and seafarer, it has afforded me the opportunity to help grow the Aircraft Center for Earth Studies. Through scientific visualization creation, 3D scientific visualizations, airborne field campaign managing, and our solar electric vessel build, I have been able to use my disparate skills for our oceans. Over the past 5 months, I have been working on our solar electric research vessel that we are calling SERVE. And you can see me here in this top picture in the bowels of the ship removing the lead acid batteries. I was the only person to fit. But I did so willingly. And this is the final product. With this vessel, we'll be able to conduct our research using sustainable energy and power our drones and other instrumentation off of that same renewable energy source. So, that leads me to what I will be doing over the summer. So my year is culminating with an internship with the ACES team, mapping coral reefs in Hawaii and Guam using 3D remote sensing aerial technology. During the field campaign, we will introduce to the communities our citizen science program called Nemo Net. So the data sets that we collect in the coral reef mapping will also go into Nemo Net that then the communities and people all over the world can interact with. Using my diverse background to help coastal communities was the driving force for me here at Rosenstiel. And to be able to see this goal come to fruition is a dream come true. So I would like to thank my professors and the Rosenstiel community for lending me their advice and time and intellect. I am beyond grateful. And I would like to thank all of you. Thank you for the opportunity to share with you my accomplishments thus far. It is only the beginning. Thank you for your time.
Thanks, Stephanie. Really appreciate your insights, and indeed, it is only the beginning, I'm sure. We established at Rosenstiel an opportunity fund to help us support different talented students, and in fact, Stephanie is one of the recent recipient of that fund. We encourage you to contact Jennifer, our Director of Advancement, if any of you has any interest to contribute to that fund. It's really used amazingly well to provide an opportunity to talented students that otherwise would not be able to come and study with us. So please consider that. That would be fantastic. It's great for us. Private universities are expensive. It is the way that it is, and we need your help to be able to support students to come work with us. It is now my true pleasure to introduce Ved Chirayath, okay, who is the speaker for this evening. Ved is the professor, the Vetlesen Professor of Earth Science, and the inaugural director of the Aircraft Center for Earth Science, or for Earth Studies, acronym is ACES, here at the Rosenstiel School. He's the founder and former director of the Laboratory for Advanced Sensing at NASA Silicon Valley and a National Geographic explorer. As a teenager, Ved discovered a planet and moved to Russia to study astrophysics. So learn Russian and moved to Russia to study astrophysics. He earned a bachelor's in physics and a master's and Ph.D. In aeronautical and astronautics from Stanford universities. His inventions include aircraft that fly on electric fields and instruments that map the oceans. Presently, he's mapping our ocean floor, especially coral reefs and shallow marine ecosystems, and authoring a new textbook on remote sensing planetary change. Ved is the 2021 National Geographic Emerging Explorer and received the American Geophysical Union 2020 Charles Falkenberg Award and the NASA Early Career for significant advances in aquatic remote sensing technology. Ved, please.
Testing, testing. Y'all can hear me well? Okay. It's a tough act to follow after Stephanie, and I think Dean Avasar has basically given you my entire presentation in a nutshell. So I'm delighted to be here. I'm so grateful to the Sea Secrets team, some of the other speakers I get to, amazing privilege to work with. You can see why I came to Erasmus from NASA after a decade. I get to work with amazing students like Stephanie, who first came to my lecture, I think, about an hour early and just said, I want to get involved, and now she's over-involved. It's fantastic. I'm super grateful. So I'm here today to share a little bit of the technologies I've been developing both at NASA and now at Erasmus. And the title of my talk is Revealing the Ocean Deep, Next Generation Sensing Technologies for Marine and Planetary Science. So I'll give you a little bit of background of who I am through some rather embarrassing photos. This is me as a kid, super interested in astronomy, trying to make telescopes out of anything I could. I loved astronomy and I loved the ocean. That's me underwater. And I also love animals. Those are all of my pets growing up. This picture I got to see from Hubble's Ultra Deep Field. They actually had a deep field picture that came out earlier. It looks at a patch of the sky about a quarter the size of the moon, and it's pretty devoid of stars. In fact, the only thing here in our galaxy is that one little star you see there. And it just stared at this area of the sky for about 30 hours and showed this picture. This is why I do what I do. I was super excited about the universe, our place in it. Are we alone? Is there life out there? There definitely has got to be something, right? We now know each star has a host of planets, just like our own solar system, and there's bound to be something. But that's really what got me excited about science when I was really small, maybe about 3 or 4 years old. And I knew then I wanted to make my own contribution and try to find worlds. So I set out trying to look for planets using a method called the photometric transit method. This is Venus passing over our sun. This is actually from 2012. And this is one way in which you can find planets. You can wait for them to slowly pass over the disk of a star and then say, oh, well, there is something that was not there before. Of course, a lot of stars are far, far away, so you cannot actually resolve the individual planet transiting the disk. But I wanted to see if I could come up with a method to do this. Around the same time, I was in high school, and I didn't have a really great upbringing. I was homeless for about 3 years of my life, and I used that time to sit on top of a mountain and do as much astronomy as I could, inventing telescopes, talking local telescope manufacturers into giving a high school kid a telescope to try to fulfill his passions. And at the time, I said, you know what? I think I can build an instrument, and I have the level of expertise to detect a planet by this DIP method, this photometric transit method. After about 3 years, I was successful in detecting a planet about 1.5 times the size of Jupiter, 150 light years away in the Pegasus constellation. If you're ever looking up at the night sky, there's a little planet there that has a large gas giant that I spent a lot of time looking at. That scholarship led me to Moscow State University, where I studied for 4.5 years in Russia, theoretical physics. That was my subway dog and my math professor. While I was there to pay the bills, I also worked as a fashion photographer for Vogue and a number of other publications, and that kind of got me exposed to the other world, very different world to theoretical physics, but nonetheless an interesting one to be in. In 2009, I transferred to Stanford University, where I started going back to the passions of astronomy and saying, what can I do with small telescopes? How can I make an impact? How can I develop new technologies that can explore our solar system? And so I took this video in 2012 of the Venus transit. This is when our planet Venus goes in front of the solar disk relative to Earth. Mercury does the same thing quite often. And at the time, I came up with a technology called atmospheric lensing that could see this at really, really high resolution. So I created these massive maps of the sun, and I didn't stop there. I tried to deploy the technology to look at other celestial objects, the sun, the moon. This was a supermoon picture I took in 2012. And NASA had been, at the same time, mapping Mars and other planets in our solar system at insanely high resolution. We're talking maybe 30-meter global pictures of these planetary bodies. And it's around that time that it sort of dawned on me, we've mapped more of the surface of all of these celestial bodies than we have of our own ocean floor, which is the majority of our planet, 70%. I was also watching one of my other passions that I cared about, the oceans, really in peril, watching them suffer as a result of climate change, anthropogenic climate change. That means human-induced climate change. We are the custodians of this planet, and on our timescale, this is happening. We're watching coral reefs die off because we're acidifying the oceans, we're heating it up by all the activity of our research, our productivity, our fashion, what have you. I wanted to somehow come back and save this one planet that we know of in our solar system that has life, and possibly the universe. The other thing about Earth's oceans that I did not realize at the time, but thanks to collaborations with Rosenstiel School, in fact, Professor Perkis here back in 2012, the oceans are, if you're studying life in general, you're looking for life in the universe, you know, we are very rare. We've been around only 4 million years on the planet. Creatures like this, called stromatolites, these have been around for 3.5 billion years. And they, in fact, created the necessary conditions for more what I would call advanced life to evolve, to breathe oxygen. So these guys still live in a hypersaline pool in Western Australia called Shark Bay. And what's interesting is if you look at our planet as a whole, 99% of the habitable volume of our world is not on land. We, again, are the exception. It's in the water. Historically, creatures like this oxygenated our planet. They were 95% of the Precambrian oxygen production, which means that when our planet first formed, it was a lot like Mars. It had 0% free oxygen. It now has close to 21, 22%, and that has given rise to organisms that use oxygen to burn fuel, right? Highly energetic creatures like us, otters, things like that. The modern equivalent, you know, stromatolites are still around, but they don't dominate the scene. We now have still most of the oxygen of our planet coming from the ocean. Some comes from land, a little bit comes from coral. But if you're, again, looking at life in general and at large scales, you need to be looking for things like stromatolites. You need to be looking for things that are capable of terraforming a planet through simple reactions, and that's been these guys. They're much more successful, I think, than humans are at climate change, despite our best efforts. So I decided at that point to combine my passions for astronomy and marine science into a career, and that's what led me ultimately to NASA and now to Rasmus. I'm interested in mapping Earth's oceans and then using what we learn to look at oceans elsewhere in our solar system. We now know of 4 icy moons of Jupiter and Saturn. Some of them are pictured here. One of my favorites is Europa up there. And we know that these moons have liquid oceans or slushy oceans, kind of like a mixture between ice and water under an ice sheet. And that's, for me, one of the most tantalizing targets to find life outside of Earth. So when I started my career at Stanford, I was developing an instrument called FluidCam and a technology called fluid lensing. That's what I'm mostly going to talk to you about today. And I'll share 2 other technologies, MiDAR and Nemo Net, that are follow-on technologies or use data sets from FluidCam and MiDAR to do citizen science, to study coral reefs and everything we have at large. All right, so the first thing I just want to share I'm not used to talking to a non-scientific group, so this is kind of fun. Remote sensing of aquatic environments is now what I do. Remote sensing means how do you study things like the ocean from space, from aircraft? Why is it so difficult? Why haven't we done this already, right? Okay, if you pull up your phone and you type in Ofu Island, you don't need to do this now, you'll see a picture like this. This is in American Samoa. It's in the middle of the Pacific. And you get a very clear picture of what's on land thanks to a series of different satellites. This is coming from Pleiades 1A. But if you try to look in the water, once you get deeper than about 5 meters, it's blue, right? So why is that? Well, there's not much light that gets down from the sun, through our atmosphere, through the water, down to what's underneath the surface. If you look at the windows in our Earth's atmosphere, there's a few gaps in the visible bands of light and the radio frequencies of light. So all of our telecommunications, your GPS, radar systems, they all operate here. A lot of radio astronomy goes on here. This is the picture through our atmosphere. Once you get into water, everything to the right of this, which is actually coincidentally the color of this laser pointer, is absorbed. So radio is absorbed, your GPS doesn't work underwater, your cell phone does not work underwater. On the left-hand side, ultraviolet and lower frequencies, or higher frequencies of light, those are also all attenuated. In water, you're really just left with blue to red is roughly what you see. And as you get deeper, it's blue, right? This is coming from scattering and attenuation. So that's the first thing. The second thing is something very simple you learn in high school, refraction. And I have a little demo I'll share with you about how this works. So if you have, this is a little tank that's half filled with water. Hopefully you can see the water there. I'm going to turn on some lasers. And you can see if the lasers are hitting the surface of the water straight down, there's no deflection in the beams, right? If we now look at the side, there is a deflection in the beams, and that's because light travels at different speeds in air and water. Now it gets more interesting if you look at the pattern that these beams make, let's say on my hand. If I shake this tank, now you'll see there's significant distortions that occur from a very small amount of wave movement, right? Okay. We're now going to take this up to the remote sensing scale and see what happens when you look at Earth's oceans from air and space. This is a picture of a small coral tank looked at from above, about 3 feet above the surface of the tank, and you can see the level of distortions that occur when you're trying to image something. Right now, the reason why you cannot pull up Google Earth and say, find something underwater, like a missing jet plane or something else, the 2 reasons are the strong attenuation, there's not much light that gets down, and the second are ocean waves significantly distort what you can see. In fact, to get a resolution anywhere less than 5 meters or finer, you need something that can correct for this refractive distortions, which is not unsurprising, right? If you try to go out and hit a fish, which hopefully you will not do, or the fish tries to hit you, it will make a correction. In fact, there's a fish that's figured this out, the triggerfish that can shoot a bug off of a leaf by making a correction for the angle. Anyone who's experienced fishing knows this. So I wanted to study this phenomena in a controlled environment. I did not have access to the wave tank at the time, so I set up a supercomputer simulation of a wave tank. And in this case, you can see there's a little profile with depth here and different test targets at different depths. And then I gave this ocean a very characteristic fluid surface, what you could see over a coral reef or out here in Key Biscayne. What you see from the top down, like again an aircraft looking at that pool, is what you'd expect to see over a swimming pool. As you get deeper in the water, it gets darker. But you also, if you slow this down, you'll notice there's some interesting phenomena going on. Ocean waves naturally form a shape, a lens shape, that can magnify and demagnify things at depth. That's very interesting to me. The second thing that you'll notice are these bright bands of light called caustics. Just like you saw those laser beams focus on my hand, ocean waves can focus sunlight down into a very bright point. In fact, if you're underwater and you look up and one of those caustics hits your eye, you get momentarily blinded. I would recommend you do not look up for reasons I'll explain later, but it's in fact very, very bright. So I wanted to develop a technology that could do, I'm going to run that one more time, that could do two things. One was to use those positive magnification events, what I call fluid lensing, to see at very high resolution, sort of use a free telescope, if you will, to see an object at depth at a scale that you would not normally be able to see. Now this is tricky because wherever there's a positive wave, there's of course the trough of the wave comes over and it demagnifies the same object. The second thing I wanted to do was to track those bright bands of light to see if I could see very deep in the water column, to use that natural focusing of sunlight that's caustic to see at a very high depth. So I created an instrument called FluidCam. This was built into a CubeSat form factor, something that we are trying to get eventually into orbit. And what this instrument does is it tries to fix these two issues of attenuation and refraction. So if we were to look at a coral test target at depth and just drain the ocean, drain this coral test tank, that's what you would see. If you now added a flat fluid to it, so this would be no ocean waves, just add on a layer of fluid, you'll see that there's absorption right with depth and it gets to be dark. Currently, this is what we're seeing from high-speed cameras. So we don't typically do this when we fly over a reef with a camera or a satellite. Most of the time we do this. We take a picture that's 1/100th of a second, and that blurs together into something you see here. This is what you'd see when you loaded up Google Earth. So fluid lensing is capable of correcting those refractive distortions, and you can see that in the top right instantaneously, and it tracks those positive magnifying events to create a picture that has very high resolution, and then it tracks those bright bands of light to create a picture that actually has much higher resolution and depth, or contrast, to the case of even a flat fluid. So the presence of ocean waves, which was something that previously caused a lot of distortions and difficulty, can actually be exploited to see very high resolution at very high depth. So I put this on aircraft, and we've been going around different coral reefs and trying to see how it works in the real world. This is from a field campaign in American Samoa. It's a beautiful fringing reef. And here you can see the view from the aircraft. So in addition to those strong refractive distortions, you also have reflection, right, coming straight back at the camera. And this would be the fluid lensing view of that same environment. So we've mapped, in this case in American Samoa, most of the island's reefs at the sub-centimeter scale. So this has been validated to about 1/2 centimeter in this case. And you can actually see some of my ocean friends here. Let's see. There's a sea cucumber that pops up. There it is. That gives you an idea of the scale. So this was 2012, 2013, 2016. We went back again, and every time I've been iterating and iterating the method. And today, I'm very excited because I get to share with you a render I worked on all weekend with Stephanie, one of the scientific visualizations showing the latest fluid lensing breakthrough at a record 45-foot depth at centimeter scale in 3D. And this is from an area in Ph.D. bomb holes in Guam. And here you can see that same with fluid lensing and without, so the original ocean wave distortions and without. And in the middle of this pier, that's where it goes down to about 48 feet in depth. We actually found a diver who dropped a rope somewhere over there, and we were able to find it in the data set and say, here you go. It's very fun. I should point out this is only rendered at 1/10 the resolution because our computer systems, despite having 400 gigabytes of RAM or so, could not handle the full data set. But when you play our video game, you can see these, and we'll show you what that looks like. So Stephanie and I are headed actually back here this summer, and we'll be remapping this area and hopefully improving upon this another 10-fold or so. So this has been really exciting for the community in Guam because for the first time they get to see their reef at really high resolution. This is the best satellite picture from before, and this is the fluid lensing result for an area that's pretty large. This is the bathymetry model for that same area, so the depth profile or topography mapped. And this is really key for understanding physical transport around an island. And that means when you have tsunami events, storm surges, hurricanes, typhoons. I have not been through a hurricane yet here, but I've been through some typhoons. You want to predict where there's going to be coastal inundation, what infrastructure will be damaged, where corals are growing that might help protect those infrastructures. And that's where these kinds of data sets come in really handy. And they improve upon the best that NOAA is doing with LiDAR and bathy sonar by a lot. And that's very costly to do using ship time. Here we can do it with aircraft. In addition, I've been urged, I guess, egged on by my colleagues in marine biology to try to not delete everything in the water column when we give them benthic maps. And so we're now introducing a product that allows us to detect the change between what fluid lensing sees the benthic surface to be, so corals mostly, things like sea cucumbers that don't move get resolved, and then to detect if anything has moved through it in the time that the sensor has imaged it. We can then see silhouettes of sharks, different types of species, and often for coral reef remote sensing, this tells you a lot about the health of the ecosystem because you don't have to painstakingly survey all the coral perhaps. You might just see a couple of keystone species that say this is healthy or this is not healthy. Okay, so now you might be thinking, well, this is great. FluidCam can maybe see the top 100 meters of the ocean surface, the depth of the photic zone, or the last point that light really illuminates the surface. But the average depth of the ocean is 4,000 meters. So there is a large way to go, right? 99% of the habitable volume is in this mess. So that's what motivated me to come up with another invention, which I called MiDAR, and this is something that NASA selected for Invention of the Year a couple of years back. And I'm really excited because now I do not have to rely on the sun, which is a very fickle thing, despite what your experience may be with it. Spectrally, it is very frustrating to work with. And MiDAR is a multispectral imaging detection and active reflectance system. So what does that mean? It means that it can see in colors that your visible eye cannot see. So in the case of MiDAR, the way it works is there's a transmitter that's a collection of laser sources, LED sources that looks kind of like this. It illuminates a special mathematical pattern upon light, and that hits an object, reflects off of it, and then the receiver, which in this case is FluidCam, can see those signals and decode what colors correspond to what pulses. It can also decode the distance to that object and other parameters. What's really exciting about MiDAR is that now in the spectrum of light that can go through the water, I can transmit in these wavelengths of light that get very attenuated because we've slowly been fixing the ozone hole, so a lot of the ultraviolet light that normally was shining through when the ozone hole was quite open are now attenuated. For marine systems, these frequencies of light hold a lot of secrets. They tell you a lot of creatures fluoresce, even on land. In the water, they do the same thing. And so we can span everywhere from the near infrared all the way down to the extreme UV using active light sources. So what this looks like in the air is you'll see one of my drones flying. Don't be alarmed. It has multiple pulses of light, and it typically looks like one white flash, but in that flash are embedded different wavelengths. And then those wavelengths can be decoded into a multispectral image. So the aircraft kind of looks like this. This has been slowed down so you can see the individual color pulses. This light reflects off of, in this case, a coral through the water, bounces back up to the receiver, and then that receiver can do some fancy math to figure out what it's actually seeing. So if we look now at the transmitter and receiver, you can see the corresponding pulses, in this case, laser pulses, onto a target. The receiver actually is black and white. It cannot detect color on its own, but it has a database of colors that allow it to correspond to different frequencies of light. And what's really fun is you can do this in about a picosecond. So you do not need to sit and look at an object and get enough sunlight and photons. You can just blast it very quickly with light and get a picture back that tells you, oh, this is what I'm looking at, and this is what it looks like in different wavelengths. So for corals, in this case a Pleiades coral, we can understand the health of that particular coral. If it's undergone bleaching stress, that's when it's zooxanthellae, it's symbiotic organisms that live inside it, jump ship because they don't like the conditions. Often when corals get bleached and then they get covered with algae, spectrally they look very similar to healthy coral. It's very hard to discern, even if you have a centimeter scale 3D model of something, is this alive or dead? But in the ultraviolet, the signal is very, very clear. It tells you, oh, this is exactly the pigment you want to see. It's not an aldol pigment. It's coming from a zooxanthellae. The other exciting thing I can do with the instrument is, in addition to imaging an object through the water, we can transmit data. So on top of this optical signal, And you won't, we slowed down the pulses so you can kind of see it individually pulsing through, but normally this again happens in about a picosecond. You can send data through the air-water interface. Now, why would you want to do that? Well, again, because GPS does not work underwater. Your cell phone does not work underwater. If you were trying to design a future NASA spacecraft to go to one of those exciting ocean moons I told you about, get under the ice sheet and send the data back, how are you going to do it? You can't use radio. You can't use, you might try hitting something and acoustically hearing it, but there's no atmosphere to propagate sound up to a spacecraft. Optically, though, you can send that data through a surface or through ice, and that's what I've been trying to develop. So in this case, we've sent the name of my former lab, NASA LAST, through the surface, but this is in the presence of ocean waves. This, for me, is very exciting because it means on Earth, eventually what we can do is create underwater robots that can map the ocean and send that data up to satellites to then downlink to us, and then we can start opening up Google Earth and finding things on the seafloor. So I'm looking at different MiDAR science applications, and right now, this summer, we'll be doing some multispectral mapping of corals, but there's different applications to deep sea imaging, looking at minerals on Mars and the moon using this instrument to try to understand what's present there. Atmospheric corrections, it keeps me up at night. It's very fun. So, field campaigns. As Stephanie mentioned, she will be leading for the first time a couple of these green dots in Hawaii and Guam, and we might actually get to Palau as well if there's time. But we've been using, different field sites around the world to both map a large diversity of coral and also as a sort of a playground to test out how well is this instrument producing data that's useful for scientists to try to understand key questions in reef biology. In addition, I've been dissatisfied with a lot of the platforms we use, so I've been investing a lot of time and energy in figuring out how to advance airborne platforms for that purpose of mapping corals and looking at deep sea targets. And so I brought one drone here. You can come up and see afterward. I will not power it on so you can touch it. And there's some other bigger aircraft that I'm hoping to bring here at Erasmus. This was a 85-foot solar electric drone that we worked through a NASA SBIR. And what's exciting about these guys, this one's sitting with my FluidCam instrument in the front. You launch them in this fashion. So this is the back of a pickup truck with a trailer off of a runway. They fly up, and then they can sit at 80,000 feet for 3 months at a time with no fuel. And so for me, as someone who worked a lot with satellites and rockets that have a tendency to explode, and then once you do get something into orbit, it lasts for 6 months, and then it will deorbit unless you have budget for propulsion to keep it in orbit. These can just sit there and loiter. And for my case, where I want to study corals, satellites do not actually see coral reefs that often. They visit an area, an island, once every orbit maybe, which is every 90 minutes, but it might be cloudy. These can sit and dwell over an island and get enough data to do fluid lensing, which I like to think of more as underwater astronomy. You're trying to get as much light as you can to see as deep as you can, and so you really need a platform like this to sit and stare. And then also you can bring your instrument down, fix it, upgrade it, make sure it's healthy. Okay, so those are the two instruments I was going to share with you tonight. And now you might be asking, centimeter scale, you're doing the math, you map an island. So let's say American Samoa is 14 square kilometers of island at sub-centimeter scale in 3D. That data set is 150 terabytes. 1 terabyte is like a good laptop, or if you have like a top-of-the-line iPhone. So imagine you go and you just do one island, and now you want to do that same island again and again and again per year, and then you want to expand it to the globe. That data set becomes massively large quickly. So we realized this about 4 or 5 years ago and came up with something called Nemo Net. And this is a very long title, the Fluid Lensing Neural Network for Global Coral Reef Assessment. Essentially, what we were trying to do with Nemo Net is teach, at the time, the NASA supercomputer, now the computing cluster here at Erasmus, how do you autonomously classify coral and just tell us what we want to know. How much of it is living, how much of it is dead, what is the species breakdown, what is the distribution of that coral. This is a tricky problem to do. I have mapped a very small portion of the Earth's surface using airborne fluid lensing at the centimeter scale, like minuscule, maybe a tiny fraction of Florida. There are global satellite data sets that have covered the whole planet, but they're much lower resolution. They do not have fluid lensing correction. They have all these ocean wave problems. So we set out to try to figure out, is there a way to just use information from this very fine scale, if we're seeing the same object, to tell the satellite layer, this is what you're seeing. So in this case, this little rock here, in a satellite picture, it's very hard to see that that's a rock, right? Spectrally, it's also quite difficult to do. So this took a lot of machine learning and training of a neural network to perform. And we learned that classification is hard. These are all unsolved problems in machine learning right now. If you open your phone and you type in Chihuahua versus blueberry muffin, computers struggle with this because to a machine learning system, these look really similar. And I trust you, if you look at these for a little while, you will confuse the two together. So early on, we learned, okay, it's not so much, you could have the most advanced machine learning system in the world, Google does, and it will still make pretty obvious mistakes. What is it that humans use that differentiates all of these objects? And in a lot of cases, it's 3D structure. It's being able to map something and see it in 3 dimensions, which if you do for all of these examples, very quickly you see they look different. They have completely different rugosities or surface roughnesses. They have different heights. They might have more spectral features you might see. And so at that point, we shifted gears and said, okay, we've finished the neural network. It runs on the supercomputer. It can classify pretty well, but it needs training input, and it needs a lot of it. We just need 1% of the data set to be trained or less, but 1% of a lot is still a lot. And so we turned to citizen science to do that. And I'll share a short video of how Nemo Net works, and then afterward you can come up and play it on this iPad or download it for your iPhone or Android or computer and help us classify corals.
What if you could help NASA create a map of the ocean floor with just the tip of your finger? The ocean, teeming with life. It defines our blue planet, drives our ecosystem, and regulates our climate. Coral reefs are one of the most diverse and important systems in the ocean. They're also becoming an important source of medicines for some of the world's deadliest diseases. But they are dying at unprecedented rates due to rising temperatures. But we don't know how much we're losing or how much our climate is changing. We can't until we determine how much healthy reef exists now. And the only way we can know that is with your help. NASA Nemo Net is a game where you classify the world's coral reefs by painting on real-life images scanned from the ocean floor using a revolutionary instrument that lets us see beneath the waves at unprecedented resolutions. Our oceans are so vast, it would take us 2 million years to classify the world's coral reefs by hand. The classifications you create are sent to our teams of NASA scientists at home base to teach our supercomputer to classify coral reefs on a global scale. Every contribution you make brings us closer to solving this problem. Join the NASA team to help us understand these amazing ecosystems. Take command of your research vessel and learn about all the different types of coral. We must keep the ocean alive. It supports our life as we know it. Together, we can create a global data set of coral reefs and build a better understanding of how to save these aquatic worlds, one piece of coral at a time. Good luck, and welcome to the NASA Nemo Net team.
So I should thank you, some of you already, because you've been playing this a lot. We've launched it 2 years ago during the peak of the pandemic. And within the first month, we had about 300 million people accessing it. We've had a sustained 100,000 players or so, and we're always looking for more, and the demographic is 6 years old to like 95. So please play. We're going to be translating into a few different languages. These are some stories that come out of it. And crucially, it is delivering ace science. So one of the biggest worries we had in the marine sensing community was, okay, how do you possibly teach a layman to classify something as complicated as a coral reef? It turns out that the children of Ph.D. trained marine biologists outperform their parents in classification accuracy. And a lot of it's because we created tutorials where they have to get a certain accuracy to progress in the game. They have to reach 95% accuracy. We give them a bunch of pre-trained data. We know the answers to it. They're labeling it, and they're doing it in 3 dimensions, which is key for our algorithm to classify those corals by itself without much supervision. So in this case, they've done algae, and in this case, Porites coral in Guam. And they're capturing all of the different boundaries. This is just their hand coloring in the game being relayed to us. And that goes then, once it's been verified, to the machine learning algorithm and lets it classify coral globally. So I'll show you kind of how that whole pipeline works. We now have data sets coming in from FluidCam, so with all the fluid distortions. That undergoes a first data processing step where we create the full 3D model of that reef, remove all the refractive distortions, see hopefully deeper and at higher resolution than you would normally see, and really get that diver scale view. All of that information, the 3D structure, the color, that's fed into Nemo Net. That's sent out into the video game. You classify one tiny little section of this, and then we can produce maps like this, where we look at the percent cover of that reef. We can see the morphology of that reef in 3 dimensions at very, very high accuracies. Prior to a lot of the work that we've been doing in 3 dimensions, the accuracies were around 40%, 50%, which again, 50% is kind of a guess. It's not really a product. And something that's been drilled into my head as a sort of recovering astrophysicist, now turned marine scientist, our life depends on organisms like this. Most of the oxygen comes out of the ocean. Most of the 21st century medicines, in fact, the leading drug to treat COVID was derived out of marine reef, a sea squirt, one of the areas that we had looked at. So we're not just doing this because these are fascinating organisms, we're doing it because it is essential to our survival. And with that, I want to say thank you, and I'd be happy to take any questions.
Thanks, Ved. It was fascinating as usual. Really appreciate it. And now I'm going to pass the microphone to Jennifer, that is going to lead the question session. Thank you.
So what we're going to do tonight is we're going to take some questions from the audience, and we're also going to take some questions from our viewers online. So what we're going to do is, can we bring up the light a little bit, and then I can see. And then if anybody has a question in the audience, if you want to raise your hand, we'll bring you a microphone by.
One thing I forgot to mention, if afterwards you'd like to come up, you can actually touch one of the 3D models we've printed from the reef. You can feel the ripples of sand on the shore and see some of the coral structures. And there's a slideshow that goes through kind of the classification and what the data set looks like. We built this mostly for the visually impaired, but it's really fun to see as well in person. So
That is amazing.
Okay. In case you're wondering, what is this weird thing that's been sitting here this time?
So we have one question here.
Hi, my name is Joe. My question is, do you think you'll be using some type of wearable technology to add to what you're doing currently? Would that help?
Do we want to add a wearable technology?
Wearables where people can also report from wherever they go diving, like they may have a watch that measures salinity or other things that can contribute to your data.
Sure. So we actually currently, Stephanie and I have our matching watches on. Oh, she took hers off because it's not fashionable. These are our underwater GPS watches, which I cannot live without, and we use it to georeference all of the data sets. We take a GPS measurement at the surface and then dive down. We do take depth measurements using the wearable technologies, and then a lot of divers that are doing routine coral surveys will take our maps underwater in an underwater case on an iPad and actually be using that iPad to find the coral that they've done their transect on, because we're the only map that exists for that underwater environment. And so that's one case where people have used their phones, I guess different types of wearables, to find where they're going, and often just to recover the instrument that they put out 2 weeks ago and they've lost. So does that answer your question? Okay.
Do we have another question from the audience?
Tim, what were the numbers on that flying drone, the amount of the altitude and the numbers of the amount of time it could stay in the sky?
So that particular one flies at 80,000 feet is the flight level, and it stays up for 3 months at a time. You can extend it or decrease it. It sort of depends on the conditions, but once you get at that altitude, you don't worry about clouds and shadows. It's just, it has to get enough solar charge during day to then slowly coast down during nighttime to about 40,000 feet, and then it boosts up again to 80,000 the next day.
It's strong enough to carry a camera.
It carries the smaller payloads that I have, so roughly the size of this drone here, but they're building a larger one. There used to be a company, AeroVironment, that built a huge flying wing that carried bigger payloads, but it catastrophically failed over a volcano once. So now there's a lot more development, but they're either called SULS, or Solar Ultra Long Endurance Unmanned Aerial Systems, which is a mouthful, or Pseudo-satellites is the other name for them, where they kind of operate like a satellite, but you don't need rocket fuel and all the infrastructure associated with that. And I just like them because they don't burn a ton of fossil fuels or explode. They might crash, but they don't explode.
We have one way back here in the top. Ask one online. It's a pretty long one, okay? It says, the MiDAR system must be limited by depth because the water will attenuate all of those nanometer scale waves by 30 meters or 40 meters. With the average depth of the ocean around 4,000 meters, it doesn't seem like there will be much benefit to coming nearly all the way up to the surface to transmit data versus just coming all the way up, or coming up all the way. What is the advantage here? Additionally, I'm unclear why optical wavelengths would be better at transmitting through ice versus RF frequencies or acoustics. Has this been demonstrated? And is there a theoretical depth limit for MiDAR?
Sure. These are great technical questions. All right, I'm going to give two answers. One is, there's a nice list of publications. One is, the one that's relevant would be the MiDAR patent and publication. I think that's number 3 and 7. And then the generic question, yes, MiDAR will not, illuminate something at 4,000 meters. But what we can do is put MiDAR on an underwater robot that can go down to depth and then map the sea floor the same way we do multispectral remote sensing on land, where we essentially use it as it's going to take a long time, but it can slowly map the sea floor in optical wavelengths. In terms of data transmission, radio frequencies do not penetrate ice very well for the same reasons they do not penetrate water very well. So that's one thing that's very difficult to, if you put something under an ice sheet and try to send that data through the ice sheet and water, you can't reach the surface because there's an ice sheet, and you have to be able to send that data up. Acoustics are a good option, except for ice. Ice will block a lot of the acoustics. And then in a lot of environments that I'm interested in, other planets that have no atmosphere, the acoustic stops at the surface, right? It does not propagate any further. Optical wavelengths, however, do propagate. And so that's one thing that we're trying to look at MiDAR for, is that it is still attenuated heavily, but if you have a powerful enough pulse, you can actually get that signal up. And then even on Earth, if you're trying to map something, a lot of submarines do not want to disclose their location. Right now, when they send data, they have to surface to send it to a satellite using radio frequencies. If they can stay submerged, you can transmit that data without surfacing. And for a lot of robots, surfacing is a dangerous endeavor. You get exposed to a bunch of other things that you don't get exposed to underwater. And you'll have experiences if you go diving and get seasick at the surface, which I do a lot. Go under, and you're no longer as seasick because the wave action gets significantly lower as you get deeper. But good questions.
Thank you.
I hope I answered all.
We have someone way up here in the back.
Yes, hello. Very fascinating technology. I'm glad that you're calling South Florida, Miami, your home, rather than Silicon Valley. But, yeah, so I'm interested to know whether you have plans to use FluidCam or what's the other technology for mapping seagrass habitats?
Yes, another seagrass enthusiast.
Yes.
They're popular in South Florida. We have mapped a few seagrass meadows in Puerto Rico as part of a campaign. A lot of the seagrass specialists want, again, sub-centimeter. They want to see the blade of seagrass in the data set. And I kind of am like, well, that's a lot of data if you survey a huge area that's just seagrass. But we are working with some seagrass experts. In fact, we just had a meeting here at Erasmus about that very topic, trying to use fluid lensing to map seagrass and understand the canopy structure. It certainly supports a ton of carbon sequestration in the ocean, so it's of a lot of interest. I haven't used MiDAR yet for seagrasses, but I know for the species identification, again, the wavelengths, it can tell you a lot of different spectral differences between the different types of seagrasses, and that's something we're trying to do here in Miami, because I also see a lot more seagrass than corals.
Okay, someone asked this question. I'm going to take one from online. It was about, this is really cool stuff. I'm up on the north central Gulf of Mexico, where we have significant river discharge. So turbidity and CDOM issues when collecting imagery. Good example of this is the Big Bend area of Florida. Can these technologies penetrate, I think it was penetrate through turbid and or brown water?
Yes, great question. I was hoping we'd ask the turbidity question. CDOM is carbon dissolved organic matter. This basically makes the water, rather than blue with depth, it starts looking brownish with depth, or brackish, right? Where I used to live in San Francisco Bay, it is a highly turbid environment. You cannot see very deep. Fluid lensing is a passive optical technology, so it does need sunlight to be able to see deep, but we have had success in turbid environments in Western Australia where there's a lot of sedimentation and mixing going on in the shallow marine system, and we have been able to resolve the structures. I'm more interested in using MiDAR to look at the wavelengths, to look through turbidity a bit more, because certain wavelengths are attenuated highly when you have CDOM in the water, and others are not. And so if you transmit wavelengths that are less scattered or less absorbed by contents in the water column, you can actually resolve something on the seafloor, despite the fact that visually you may look at it and see nothing. So I am trying to test here in, what's it called, Bear Cut, to see if we can see some of that seafloor, and there's a lot of critters that live down there, to see if we can see through some of that turbidity and employ more astronomy techniques with MiDAR and fluid lensing to get around the turbidity issue. But it is a problem. Eventually, if you kick up enough CDOM or marine snow or something else in the water, it is hard to see through.
Do we have another question in the audience here? We'll go with this one back in the back here. We want to wait for the microphone, please.
How do you deal with the conflict between looking at the universe, which tells us about the past, and looking at the ocean, which is really predicting our future?
Yes. So one of my life goals had always been to be an astronaut. It still is. In fact, last year I was a finalist for the program. And one of the things I realized when I got to do this job was I get to be an astronaut on the coolest planet that we have found. And believe me, we've spent a lot of time looking for life on Mars, on the moon, on different planetary bodies. And there's not much there, despite what some of my geologist friends may say. I find them pretty empty worlds. So for me, if this is the only spot that we know of in the local universe, in the distant universe that has intelligent life, or life, I should say, this is where I want to be, and this is what I want to study. And I get as excited about the deep sea as I do about space, because it goes to that human passion of wanting to just know what's around that corner. What's the next step? And we haven't finished here. We can't go and explore all these other worlds if we don't know how our own works really well. So that's kind of what I get excited about. We got a pause for
Well, we are about 15 seconds from 8 o'clock, and I wanted to say that will be our final question. Can people reach you and get information if they have more questions? Also, this will be on our YouTube channel in the coming days, and also on our Facebook channel if you'd like to see it or you'd like to share it with friends. And thank you so much for coming. If you are interested in helping us with our mission, please visit our website. It's rsmas.miami.edu. Thank you, and have a good night.